Hi everyone, welcome back. In this lecture we're going to look at the concept of continuity. We're going to break this lecture up into two parts actually. The first part we're going to look at the definition of continuity, and then the second part we're going to look at some consequences of that definition and one extremely important property that continuous functions have, namely the intermediate value theorem. Okay, so let's get started. Continuity. Okay, that term is a very common everyday term. We sort of have some informal idea of what the term means in certain contexts. So for example, if I said, my coach made me run continuously around the track for an hour, you automatically imagine me running around the track without stopping, without breaking, just continuously running. So that's sort of our informal idea of continuity. What we need to do in mathematics, though, is we take these informal terms, we start using them, but we need to give them a precise technical meaning. And so for us, part of the start of this lecture is giving a technical mathematical meaning to the word continuity. So let's look at these two graphs. What is the difference between these two graphs? Can we sort of characterize what's happening? Well, you might immediately say, well, one's continuous and one's not. But of course, we're using some sort of informal idea of continuity, so continuation without breaking, that kind of stuff. But can we say it in other terms? Well, you may say, well, the second one, the one on the right, has a break in it. There seems to be a break right here. Whatever that means, the graph is broken in some sense. Well, we're sort of honing in on what the idea is. It's not that the fact that it's broken in some sense, but it's, if I were to draw this graph, then what would happen? Well, I would be sketching, 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 and then at some point, I'd have to lift my pencil in order to continue sketching. So I guess that's kind of what we mean by it has a break in it. We have to lift our pencil up in order to continue sketching it. On the other hand, the one on the left, I can sketch, sketch, sketch all the way along and not have to lift my pencil up. So in some sense, I've continuously drawn the curve. There again, I'm using the informal idea of continuity. Okay, so we've got this informal notion. Now let's tighten it up. And the nice thing is we have limits, and limits are going to be great to sort of tighten up this technical word continuity. So let's look at our definition. A function is continuous at a number a if the limit as x goes to a of f of x is exactly equal to the function value. Okay, so this is saying, remember that the limit, this part over here, is talking about what's going on around a. This part over here, the function value, is talking about what's exactly happening at a. So this, in some context, is trying to grab the fact that what's going on around the x value of a for the function matches up with what's going on exactly at the function value at a. Okay, so there is a little bit packed into this statement here. It looks like a one-liner, but there's really three things that are going on. The first thing is, in order for the right-hand side of the equality to make sense, f of a, we need that a is in the domain of f. Okay, so a has to be in the domain. What next? Well, in order for the left-hand side to make sense in this equality, we need that the limit exists. And then this equality is really saying that those two things are equal. So we need these three things in order for continuity to hold. And that's what's really encapsulated by this one statement. The limit better exist, the function value better exist, and those two better match up. And if they do, then the function's continuous at the point A. So let's look at an example of this. Here is a curve. Maybe it's doing something like this. Got a little hole in it, continues on, and my function value is defined to be some other value there. What part of the definition of continuity is this failing? So certainly this is discontinuous in our informal sense because I had to lift my pencil, but is our definition capturing that? And if it captured that, what part of the definition failed for this example? Why can we see it's discontinuous? Well, what do we have? Let's call this a. We have that the limit as x goes to a of f of x. Well, that looks like it exists, so that's fine. Is a in the domain of the function? Sure. It takes on this value, whatever it is. I haven't filled that in, but it's not necessary. It takes on some value. So we also have that f of a exists. Are they equal? Well, no, they're not equal. F of a is not the same as the limit as x goes to a of f of x. So they just happen to be different. So f is not continuous at x equals a. Okay, so these are the things we're going to have to check. As I said, there's a lot packed in that one statement. These are really these three items. Of course, that second item B, that the limit exists, really means that both the left-hand and right-hand limits exist and they are equal to each other. We saw this when we were defining limits in the first place. So there are a number of things to check to make sure they all match up in order to get continuity at the point. So let's look at a more formal definition then of what a discontinuity is. I sort of used it already, but discontinuity, well, a function's discontinuous if it's not continuous. But there needs to be a little bit more. There has to be some substance to the function. So the function better be defined on an open interval containing a. Once the function's defined on that open interval containing the point a, if the limit as x goes to a of f of x does not equal f of a, then it's not continuous there. And we say it's the function's discontinuous at x equals a. So let's look at a bunch of examples. In this first case, we want to determine where is the function discontinuous. Well, let's have a look. It's a piecewise defined function. There's really something that's going on at 2. Everywhere where x is not 2, we're using this expression for the function. When x is equal to 2, the function value takes the value 5 on. And the reason we are defining it to be different when x is 2 is because this expression is not valid when x is 2. I can't plug 2 in because I get a denominator of 0. Okay, so we want to see where the following function is discontinuous. That means we really want to check all of the possible x values individually in some sense to see if they're continuous or not. So the limit as x goes to each possible x value a is the limit of f of x as x goes to a equal to f of a. So let's break some cases down now. We've got something special going on at 2, so let's leave that aside for a second. Let's suppose we're taking a limit as x goes to a, so let's suppose that a is not 2, and we'll look at the limit as x goes to a, f of x, and compute what that is. So this is the limit as x goes to a. Well, when x is not equal to 2, we know that f of x is expressed in terms of this rational function. So we're looking at this limit. Now, as x goes to a, remember a is not equal to 2, so the denominator, the limit won't be 0. As x goes to a, x minus 2 would be going to a minus 2. As x goes to a, the numerator would be going to a squared minus 4. So we're essentially using the properties of limits that says if we're looking at the limit of a ratio, it's just the ratio of the limits, provided the denominator isn't 0. And it's not in this case because of our assumption that a is not 2. So this becomes a squared minus 4 over a minus 2. That just happens to be the function value at a. And therefore, the limit as x goes to a of f of x is equal to f of a. So f is continuous at x equals a, where a is not 2. So at all values of a, f is continuous, except possibly at 2. We haven't checked that one yet. So let's go ahead and check that one. For a equal to 2, is the function continuous there? Well, what we need to do is we need to work out the limit as x goes to 2 of f of x. Okay, so x is getting closer and closer to 2, never equal to 2. So the expression for f of x can be replaced with x squared minus 4 over x minus 2. What's going on as x goes to 2? Well, the numerator is going to 0. The denominator is going to 0. What is the limit? Well, we have more work to do. It's of type 0 over 0, so we're going to see if we can try to simplify the expression first before we compute the limit. So let's go ahead and work on simplifying this. It's really the x minus 2 in the denominator that's causing a problem. There also happens to be an x minus 2 factor in the numerator, which I can use to cancel that out. So we'll factor the numerator, x minus 2, x plus 2, all over the denominator, x minus 2. As x heads towards 2, notice x is never equal to 2, so x minus 2 and x minus 2, they're never equal to 0 for these x values. The limit's talking about what's going on near 2, not at 2. So these things cancel off. We get then that it's the limit as x goes to 2 of x plus 2. And what's the limit of this? Well, as x goes to 2, x plus 2 gets close to 4. So here the limit as x goes to 2 of f of x is 4, but what is our function value at 2? Our function value is, scan up, at 2 the function value is 5. So the limit as x goes to 2 of f of x is not equal to the function value. The limit is 4, the function value is 5. And so f is discontinuous at x equals 2. So let's get a rough sketch of this just to see what's actually going on here. We saw in our calculations that we could take f of x and this rational expression for it and rewrite it as just x plus 2 when x is not equal to 2. So what that means is our function looks like the linear function x plus 2, except when x is 2, there's a hole there. But that hole is filled in by the other piece of the function. Well, the hole isn't filled in, but the function value does assume a value when x is 2. It's actually the value of 5. So here there's a value of 4, because that's essentially lives on the linear function x plus 2. And up here, our value of our function is 5. So now we can see why it's discontinuous. Continuous everywhere else, because I can essentially draw it without lifting my pencil. But at 2, the function takes a jump and then comes back down. So one way to look at it is if the person who came up with this function really wanted a continuous function, they probably shouldn't have defined it to be 5 when x is 2. They should have defined it to be 4 when x is 2. So we call this kind of discontinuity that we've just found here a removable discontinuity. And the reason we call it a removable discontinuity is because we can remove it by just redefining the function at a single point. If I redefine the function at the x value of 2 to be 4 instead of 5, then this would be a continuous function. And in fact, it would just be the linear function x plus 2. Okay, let's look at another example. Again, there's a piecewise defined function here. One of the pieces is 1 over x minus 2 when x is not 2, and the other piece is 5 when x is equal to 2. Again, for x not equal to 2, we can look to see is the function continuous for those values. Well, as x goes to, sorry, my apologies, for a not equal to 2, we're looking at continuity at a particular value of a. So for a value of a not equal to 2, what's the limit as x goes to a of f of x? Well, that's the limit as x goes to a of 1 over x minus 2. As x gets close to a, x minus 2 gets close to a minus 2, which is not 0. So this gets close to 1 over a minus 2, which just happens to be the function value of f of a. So f is continuous at x equals a when a is not equal to 2. What about the case when a is 2? Looking at this, it seems to be that that's, if any place there's a discontinuity, it's probably going to be there, because for a not equal to 2, we're just staring really at the rational function 1 over x minus 2, and since we're not considering x to be 2, there really doesn't seem to be any problems with that function. So it really seems to be where we're doing the gluing. We're gluing this piece to that piece, which is happening at x equals 2. It seems to be that's the place that a possible discontinuity can arise. So let's check it. Limit as x goes to 2. Okay, so a little bit of foresight here. We've seen limits as x goes to 2 of 1 over x minus 2 before, and there it made sense to consider left and right hand limits, so we'll go jump straight for that. I'm going to consider the left hand limit, and I'm going to consider the right hand limit. If you're still wondering why, you'll see in a second why we're going to break it up into these two limits. Limit as x goes to 2 from the left. Well, that's the limit as x goes to 2 from the left of 1 over x minus 2. As x gets close to 2 from values slightly smaller than 2, x minus 2 is getting close to 0 through negative values. So 1 over a small negative is heading towards a big negative. So this limit is going to be negative infinity. Similarly, as x goes to 2 from the right of 1 over x minus 2. We're heading to 2 from values slightly bigger than 2. X minus 2 is heading to 0 from values slightly bigger than 0. So these are getting small in the positive. 1 over a small positive is a big positive, so this is heading off to infinity. Now, the left and right hand limits don't exist. So the limit in general does not exist. So f is continuous at x values equal to a, where a is not equal to 2, and when a is 2, f is not continuous at x equals 2. And the reason it's not continuous here is the limit doesn't exist. We just found that the limit doesn't exist. The function value exists, it's 5, but the limit doesn't exist. Let's get a rough sketch of this. X equals 2 seems to be where the problem is. So what's going on there? Well, we notice that as we head towards 2 from the left, we're heading down to negative infinity. As we head towards 2 from the right, we're blowing up to positive infinity. So the function looks something like this. And when x is 2, it takes on a value of 5. So in some sense, we've again managed to capture the idea that we had to lift our pencil to continue drawing this curve. It's discontinuous, and we pick that discontinuity up by considering limits and function values. This particular discontinuity has a name, and it's called an infinite discontinuity. So let's look at another example. In this example, again, we have a piecewise defined function. Let's get a sketch of what it looks like. The domain is from 1, including 1, to 3, not including 3. So we're starting here at 1, we're heading off to 3. On the interval from 1 to 2, it takes on a value of 1. So from 1 out to 2, it takes a value of 1 on, but 2 is not included in this part of the domain. So we have an open point there. The next interval from 2 to 3, it takes on a value of 2. So it looks like this. An open one there with a height of 2. So there's the sketch of our function. Looks to be continuous everywhere except possibly at 2. Why is it discontinuous at 2? In terms of our definition, well, the limit as x goes to 2 of h of x, in this case, doesn't exist. Why doesn't it exist? It doesn't exist because the left-hand limit doesn't equal the right-hand limit. So we can say that the limit as x goes to 2 from the left of h of x is 1, and the limit as x goes to 2 from the right of h of x is 2. These are not equal to each other, notice. So the limit in general does not exist. And so h is not continuous or discontinuous at x equals 2. We call this kind of discontinuity a jump discontinuity. One of the things to note about this, though, is around 2, notice that if we look at the, maybe I'll put this in a different color just because it's sort of a side note here. So notice, if I just look at the right-hand limit as x goes to 2 from the right, f of x, what does that equal to? Well, as we head towards 2 from the right, the function, the limit is going towards 2. That just happens to be the function value there. So this kind of almost looks like the definition of continuity, except it's just a one-sided limit rather than a general two-sided limit. So in this case, we could say, well, it's not continuous there, but it is continuous from the right. The function's continuous from the right there. We could say that, and that leads to our next definition. A function is continuous from the right if the limit as x goes towards a from the right is equal to the function value there. We could also say it's continuous from the left in a similar fashion. So this just extends the idea of continuity to the endpoints of intervals. And so we can say that a function is continuous on an entire interval if it's continuous at each point in the interval, which is what we've defined, continuity at a point. So if it's continuous at each point on an interval, it's defined to be continuous on the entire interval, where the interval may have some endpoints, in which case we say continuity at the endpoint is really either this left or right-hand continuity when we're at the endpoint itself. So for example, if I'm looking at a function that looks like this, it's very similar to the one we just had. Maybe it looks like this and like this. Where is it continuous? Well, that's A, that's B, and that's C. What intervals would it be continuous on? Well, it's continuous on, for example, the interval from B to C. It's continuous on that interval. It's continuous on the interval from A to B, as long as I don't include B in the interval, because something sort of funny is happening at B. There's a jump happening at B, but if I don't include B in the interval, then I get continuity there. I get continuity on this interval from A, including A, to B. Where is it discontinuous or not continuous? It's not continuous on what intervals? Well, it's not continuous on the closed interval from A to B. Here I'm going to include B. It's not continuous there because it's continuous at all these points. The problem is it's not continuous at B because the left-hand limit at B goes to the height of this hole, whereas the function value at B is the height of that point. So the left-hand limit at B doesn't equal the function value there. So it wouldn't be continuous on that interval. It's certainly not continuous on the whole interval from A to C either, because there's that jump discontinuity in the middle. Okay, let's look at another example. Here we want to find a number C that makes the function f of x continuous everywhere. So again, it's one of our piecewise defined functions. It's likely then that the problem of discontinuity is going to happen where we're sort of gluing these pieces together. That's at x equals 1. Certainly this x to the 4th minus 1 over x cubed minus 1, that seems to be continuous on all values not equal to 1, since if I'm looking at the limit as x goes to a value not equal to 1, I can certainly plug it in top and bottom because I don't have to worry about the denominator vanishing there. So the issue seems to be at 1. So let's look at, consider a equals 1, consider that as the point we're going to look at. We're going to look at the limit as x goes to 1 of f of x, and we're going to see, does that equal the function value? Well, the limit as x goes to 1 of f of x, that's the limit as x goes to 1 of x to the 4th minus 1 over x cubed minus 1. Okay, so how do I calculate this limit? Well, as x goes to 1, the denominator is going to 0, the numerator is going to 0. This is type 0 over 0. So we're going to have to do some algebraic manipulations to try to get some sort of common factor between the two to cancel out and get an equivalent expression for this when x isn't equal to 1. We can do that by noticing that they're both polynomials, top and bottom. X minus 1 is a root of both of them, so I can always factor an x minus 1 out of each. What's left over when I factor? Well, now we can just, you can do long division, polynomial long division here, x to the 4th minus 1. Divide out an x minus 1, and what you're left over with is an x cubed plus an x squared plus an x plus a 1. make that a little bit bigger there, plus a 1. Similarly on the bottom, factor out x minus 1, that leaves you with an x squared plus x plus 1. And now we can get rid of those x minus 1s, since the limit's only caring about what's going on around 1, not exactly at 1. So this expression and the one I get by canceling are behaving exactly the same at values near 1, but not at 1. So now it's the limit as x goes to 1 of x cubed plus x squared plus x plus 1 over x squared plus x plus 1. And so that has a value of 4/3, just plugging 1 in. So the limit as x goes to 1 is 4/3. What's our function value at 1? Well, that is c. To be continuous, I want the limit to be the same as the function value. So f is continuous at x equals 1 if c is equal to 4/3. And so there we go. We found our value that makes the function continuous at 1. And then, as I mentioned, it's continuous everywhere else because that's just this piece, this rational piece, which is continuous at the other values, not equal to 1. Okay, so what actually was going on here? Well, we can look at sort of a sketch of this. Here I've got that c value. I'm letting it change. For different values of c, we get sort of all these different functions here. We want to find the one which is continuous. So that means we want to find the value of c for which that point fills the hole. Where does it fill the hole? Well, it's sort of close around, 1.3. So I'm not able to hit it exactly, so I'm just going to type it in. So when c is 4/3, that fills the hole, and that's what we found here. If we take that c value to be 4/3, we filled the hole, and now it's a continuous function. Okay, so we've introduced the concept of continuity, gave it a technical meaning. So continuity in mathematics is a very technical term. It's defined in terms of this limit equaling the function value. We've done some examples now. Next lecture, we're going to look at some consequences of the definition of continuity and one of the main theorems about continuous functions. This is the intermediate value theorem. All right, we'll see you next lecture.